Volumetric analysis is a common laboratory method of quantitative analysis that can be used to determine the concentration of a known reactant. The term titrometric analysis is more commonly used today to refer to volumetric analyses carried out by way of titrations. Titrometric analysis is carried out by determining the volume of a solution of accurately known concentration, which is required to react quantitatively with an accurately measured volume of the substance to be determined. This is the analyte. The reactant of accurately known concentration is referred to as the standard solution. The standard solution is usually used to fill a burette and is referred to as the titrant. The analyte is usually measured into an Erlenmeyer flask, also known as a conical flask, using a pipette. Titration involves adding the solution from the burette to the solution in the conical flask until the reaction is complete. The substance being titrated is often referred to as the titrand. The point at which the reaction is complete is known as the endpoint. For acid-base titrations, it is the point at which no more neutralization can take place and is indicated by a distinct color change of the indicator. Indicators commonly used include screened methyl orange, and phenolphthalein. Volumetric analysis is carried out by performing a series of titrations. Titrations can be between an acid and an alkali or carbonate solution. The endpoint is determined by the color change of an indicator, or in the case of a thermometric titration, using a thermometer by determining the volume that corresponds to the highest temperature of the reaction, usually determined graphically. An oxidizing agent and a reducing agent, the endpoint is determined by a sudden color change in one of the reactants. The apparatus commonly used in volumetric analysis include a pipette, a burette, and volumetric flask. These measuring devices provide a much higher degree of accuracy than measuring cylinders, while beakers and conical flasks give only approximate measurements. By employing pipettes, burettes, and volumetric flasks, the results of titrometric analyses will be reliable enough for most scientific work. The concentration of a solution is the amount of solute contained in a given volume of solution. The volume of solution is usually 1 dm cube or 1 liter, and the amount of solute is normally expressed in units of mass, usually grams or moles. The concentration of a solution may be expressed in grams per dm cube, called the mass concentration, or moles per dm cube, called the molarity or molar concentration, abbreviated with a capital M. Given that most apparatus for measuring the volumes of liquids is calibrated in centimeters cube or milliliter or liter, it is important that one can freely convert from one unit into the other. 1000 cm cube is equal to 1 dm cube. Given that 1 dm cube is equal to 1 liter and 1000 milliliter is equal to 1 liter, then 1000 milliliter is going to be equal to 1 dm cube. Hence, a milliliter and a centimeter cube represent the same volume and are therefore equal. In order to convert 1 dm cubed to cm cubed, one must multiply by 1,000. Finally, moles per liter is equal to moles per dm cubed. Another conversion that is an absolute necessity is the ability to convert from grams per dm cubed to moles per dm cubed and vice versa. Given that volume is expressed in the same unit in the units of concentration, then it becomes a matter of merely converting given mass in grams to moles. Hence, to convert from grams per dm cubed to mole per dm cubed, simply divide by the molar mass of the compound in question. And to convert from moles per dm cubed to grams per dm cubed, multiply by the molar mass of the compound in question. Example 1. Convert 0.125 moles per dm cubed of sodium hydroxide to grams per dm cubed. Multiply 0.125 by the molar mass of NaOH. Hence, 0.125 moles per dm cubed of sodium hydroxide is equal to 5 grams per dm cubed. Example 2. Convert 24.5 grams per dm cubed of sulfuric acid to moles per dm cubed. Divide 24.5 by the molar mass of H2SO4. Hence, 24.5 grams per dm cubed of sulfuric acid is equal to 0.25 moles per dm cubed. You must also be able to calculate the number of moles of solute that are contained in a given volume of a solution of a particular concentration. Example 3. Calculate the number of moles of hydrochloric acid that are contained in 20 cm cubed of a 0.12 molar solution. First, recall that 0.12 molar is 0.12 moles per dm cubed. Second, write the molarity as a statement. Relation, calculate by simple proportion the number of moles of hydrochloric acid in 20 cm cubed of solution. The number of moles of hydrochloric acid in 1 cm cubed of solution equals 0.12 mole divided by 1,000. Therefore, the number of moles of hydrochloric acid in 20 cm cubed of solution equals 0.12 mole times 20 divided by 1,000. This is equal to 0.0024 moles. Using titration to determine the mole ratio in which reactants combine can be done if the concentration of both titrant and titrand are known. In order to determine the mole ratio in which two reactants combine, the number of moles of each substance used must first be determined. After which, the values for each will be used to make a sentence which will express the mole ratio in which the reactants combined. Example, 0.02 mole of MOH2 reacts with 0.01 mole of HX. Example, 25 cm cube of sodium hydroxide solution of concentration 0.8 moles per dm cube neutralizes 20 cm cube of an acid H2SO4 which contains 0.5 moles per dm cube. A. Determine the mole ratio in which sodium hydroxide and sulfuric acid combine. B. Write an equation for the reaction. Solution. Number of moles of sodium hydroxide used, 1000 cm cube of sodium hydroxide solution contains 0.8 moles. Therefore, 25 cm cube contains 0.8 divided by 1000 times 25, which is equal to 0.02 moles. Number of moles of H2SO4 used, 1000 cm cube of H2SO4 solution contains 0.5 moles. Therefore, 20 cm cube contains 0.5 divided by 1000 times 20, which is equal to 0.01 moles. 0.02 moles of sodium hydroxide reacts with 0.01 moles of sulfuric acid. Converting to whole number ratios, then 2 moles of sodium hydroxide react with 1 mole of sulfuric acid. Therefore, B. Equation 2NaOH aqueous plus H2SO4 aqueous gives Na2SO4 aqueous plus 2H2O liquid. Standardized sodium hydroxide and sulfuric acid is H2SO4 aqueous plus 2NaOH aqueous to give Na2SO4 aqueous plus 2H2O liquid. The concentration of the base would be known based on the fact that it is standardized. A known volume of the acid would be titrated with the base. The volume of the base used would be used to calculate the number of moles that is contained in that volume. For example, if the original concentration of the base was 0.01 moles in 1000 cm cube and 28 cm cube of the base reacted with 25 cm cube of the acid, calculate the number of moles contained in the 28 cm cube of base. If 1000 cm cube sodium hydroxide contains 0.01 moles, then 1 cm cube of NaOH contains 0.01 moles divided by 1000 cm cube. Therefore, 28 cm cube will contain 28 cm cube times 0.01 moles divided by 1000 cm cube of NaOH. This is equal to 0.0028 moles. The cm cube unit will cancel out each other and the value will be in terms of moles. Let's look at the reaction equation. H2SO4 aqueous plus 2NaOH aqueous gives Na2SO4 aqueous plus 2H2O liquid. Based on the equation above, the mole ratio of acid to base is 1 to 2. Therefore, the 25 cm cube of the acid will contain half of the number of moles that is contained in the 28 cm cube of the base. Therefore, the 25 cm cube of acid contains 0.0028 moles divided by 2, which is equal to 0.0014 moles. .0 grams per dm cube sodium carbonate that has been contaminated with sodium chloride. Solution B contains 5.8 grams per dm cube of nitric acid. 25 cm cube of solution A required 21 cm cube of solution B for complete neutralization. Calculate the percentage purity of the sodium carbonate used to make the solution. Solution. Step 1. Identify the reactant for which both the concentration and reactant volume are provided. HNO3. Step 2. If concentration is given in a unit other than moles per dm cube, convert to moles per dm cube, then calculate the number of moles of reactant contained in the given volume of solution. Converting mass concentration of nitric acid to molarity. Molar mass of HNO3 is equal to 63 grams per mole, which is equal to grams per dm cube. For the reaction, 2HNO3 aqueous plus Na2CO3 aqueous will give 2NaNO3 aqueous plus H2O liquid. Step 4. Determine which reactant or reactants or product or products the question is concerned with, and from the balanced equation, determine the simplest mole ratio between the reactant identified in step 1 and the substance of interest. Mole ratio. 2HNO3 to Na2CO3 is 2:1. Step 5. Given the mole ratio, calculate the number of moles of the reactant or product of interest. If 2 moles of HNO3 react with 1 mole of Na2CO3, using the volume of the reactant or product of interest and the number of moles calculated in step 5, calculate the concentration of the substance of interest in moles per dm cube and, if necessary, in grams per dm cube. Concentration of Na2CO3. carbonate divided by the mass of the mixture of sodium carbonate and sodium chloride times 100. Percentage purity of mixture is therefore equal to We've come to the end of part 2 of mole concept. As in any area involving calculations, the best way to master these concepts is to constantly practice. So until our next lesson, practice, practice, practice.